This is lesson 1.5 on page 40. We're going to go ahead and run through all the examples, just kind of talk about the big idea of what lesson 1.5 is all about, as well as the practice problems that are on page 45. We're going to do 9 through 29. Those go a little bit quicker than you'd think. 9 through 29 sounds like a lot of problems, and it kind of is, but we're going to actually just graph them and interpret the answers from that. So it's not actually a lot of work that you're writing down. So this lesson is all about if you have an equation or an inequality, either one, you can learn a lot of information. You can basically solve it just by graphing the problem. Just to be clear, an equation is something like this with example number 1, negative 3x plus 20 equals 5. So an equation has to have an equal sign. And then an inequality is something like with example 2 here, x squared minus 4 is greater than 0. So an inequality would actually have an inequality sign. Greater than, less than, greater than or equal to, less than or equal to. So those are the main differences between the two. Equation has an equal sign. Inequality has an inequality sign. So example 1, use a graph to solve this equation. So they're telling you negative 3x plus 20 equals 5. A couple ways you can do this. You can graph it by hand. That's just a linear function. I know that because that's negative 3x. That's just an x to the first. So anytime your variable is to the first power, it's just a linear function. It's just a straight line. And you could see that example right down here, the blue line with example 1. That's negative 3x plus 20. Then on the other side, they've got 5. So what this essentially is a compound equation. It's got two separate, I guess you can call them functions, compounded into one equation. So the left side is one of the equations that you're going to graph, one of the lines you're going to graph. Then the right side is the other line. So think about this as two separate steps. So they've got them color-coded down here. Negative 3x plus 20 is the blue line. 5, that's the red line. You can also think about this as y equals negative 3x plus 20 and y equals 5. If that helps you, just splitting up the left and the right side as two separate functions. And that's essentially what they're telling you here in the tutorial that they're walking you through. Here's where they graph the problem. Again, you can graph it by hand, which is definitely the longer way. You can graph it using a graphing calculator if you have one at home. I personally would recommend Desmos. Envision has Desmos embedded under the math tools that you can just click on, and then it takes you right to Desmos. I've also embedded a link to the Desmos graphing calculator in Canvas. So if you just access Canvas in the lesson or in the section 1.5 for this week, you can just access that Desmos calculator that way. Or just go Google Desmos graphing calculator. It's the first link that pops up. So here's the two lines graphed. The important thing here, the information you're taking away is wherever they cross each other. So if you have an equation, the solution to that is wherever those two lines, wherever those two functions cross each other. So in this case, it looks like when x is 5, our y value is 5. So at 5 comma 5, that's the solution to that equation. Negative 3x plus 20 equals 5, where they both cross each other. Here's another example at the top of page 41. So now they've got a couple different types of problems, or a couple different types. One's absolute value, one's a linear function. So absolute value is always denoted with those kind of straight up and down lines. It's inside almost like a grouping symbol. And then again, linear functions, that's an x to the first power. So I'm going to graph the absolute value function. I'm going to graph the linear function. And again, wherever those two functions cross, it could be one place, it could be two places, it could be an infinite amount of places if it's the same function. Those are the answers. Those are the solutions to that. Here's the example. The blue function, that v is the absolute value. The red line, that's my linear function. It looks like they cross at 2 comma 2. and also at 10, 6. So 2, 2, 10, 6. Those would be my two answers for this problem with B. If you just wanted to write x equals 2 and x equals 10, that's sufficient. I like to give the actual point. So I would say if I were writing this out, 2, 2, 10, 6. Example 2. Solve a one variable inequality. So one variable just literally means it has one single variable. You're not going to see x and y and z or a and b. You're going to see just one variable in that problem. Solve that by inequality by graphing. So same as before, we're going to graph these inequalities. But now instead of where they overlap, now you have to take into account the greater than or less than, greater than or equal to, less than or equal to. So it looks a little bit different. So x squared minus 4, that is going to be the parabola. And it's hard to see it here, but I will try to point it out. The right side of that inequality is y equals 0. And when y equals 0 is that x-axis. It's right underneath my pencil. So it's right here. They don't have it labeled with any type of color or anything, but it's a flat line at y equals 0. But what they really want, what they're pushing for, is when is this parabola specifically greater than 0? So I only want to keep the part of the parabola that's greater than 0. So let me, oh man, I don't really want to write on my book. I'll just write with a pencil. So here's my line, y equals 0. It just goes left to right, just like that. So I only want to keep the part of this parabola that's greater than that line. We'll take a look. At this x-intercept right here, -2, 0, if I go to the left, it looks like that parabola is above that line. It's greater than that line. When they say greater than, they're talking y values. So greater is above it. What about between these two x-intercepts? Well, like right here, it looks like my parabola is less than, because I have to go down to hit that parabola. Same thing with the, I don't know, at +1. It looks like I'm going down to hit my parabola. So between those two x values, it looks like my parabola is less than that line, y equals 0. But now once we cross this other x-intercept of +2, it looks like it's back up above it. If I go to something like 2.5, it looks like it's going up. It's greater than that line. So here, the parts we want to keep are all of my x values that are less than -2. So everything to the left of -2. Again, because every x value to the left of -2 will always go up to hit my parabola. The other part that I want to keep is all of my x values that are greater than 2. Because as soon as I get a number greater than 2, I'm going to go up to hit my function. But if I choose an x value between -2 and 2, every single time I'm going to go down. It's going to be less than that line. So I don't want to keep anything between -2 and 2. I just want to keep all my x values that are less than -2 and all my x values that are greater than +2, because that's where I go up. That's where I'm greater than that line to hit that function. So this, I'm assuming, is talking about the same thing. For part B, a motorcycle is 40 miles ahead of a car. The motorcycle travels at an average rate of 40 miles per hour. The car travels at an average rate of 60 miles per hour. When will the car be ahead of the motorcycle? So they're going to have a piece of this function that's talking about the car and a piece that's talking about the motorcycle. So let me just clarify here. Sometimes I like to read these things again. A motorcycle is 40 miles ahead of the car, right? And they show that in the picture. The motorcycle is 40 miles ahead of this car. The motorcycle is going at an average rate of 40 miles per hour. the car is going at an average rate of 60 miles per hour. So motorcycles in front of the car, the motorcycle goes 40 miles per hour, the car goes 60 miles per hour. So let's see what that function looks like. So they're saying the motorcycle is represented with the red function, or the red piece of that inequality. The car is represented with the blue piece. So let me show you exactly where that information is coming from. The motorcycle, again, started off 40 miles ahead of the car. So that's why the plus 40 is there. And then it's going 40 miles per hour. So 40x plus 40, that's how they come up with that piece. And then the car, they're just saying, is going 60 miles per hour. So 60x, 60 times x. So the blue piece, the car, that's represented with the blue line. The red piece, which is the motorcycle, that's represented with the red line. And you can see, based off of graphing these two separate lines, it looks like they cross at about 2, man, I'm going to say about 125, okay? But that's not the piece we want, because look at this. This is an inequality. So we don't necessarily want just the piece where they're crossing. We want every piece of this function when the blue line is greater. Another word for greater is higher, literally higher than the red line. So whenever the blue line is greater than the red line. Well, it looks to me like as soon as you hit that point where they cross and after, that blue line is always higher than that red line, right? Forever. It never stops going. But before they cross, before they intersect, the blue line is always less than the red line. So that's what we want to keep. We want to keep every x value that's after this point where they cross, because that's when that blue line is always strictly greater than that red line. They're saying the intersection appears to be 2, 120. So for me, my answer, when is that blue line going to be greater than the red line? I would say every x value that's greater than 2. Which is what they're kind of writing down here in words. If I was to write it out, I would say this: x is greater than 2. Don't be like me. Don't write in your book. So x is greater than 2. Let me erase it before I forget about that. Example 3. Use a table to solve an equation. Use a graph and tables to solve this equation. X squared minus 4x plus 1 equals x minus 2. Again, in this section, what they're trying to push you to do is to recognize that the left side of that equation is one function, the right side of that equation is another. So this is y equals x squared minus 4x plus 1. This is y equals x minus 2. So you can see the left side, the x squared part, that's the red function. The x minus 2, that looks like it's going to be the blue function. So if I sketch those graphs, if I type them in a graphing calculator, they should look something like this. It looks like you can kind of visually see when those functions are crossing. That's going to be, I don't know, about 0.8 comma negative 1.2 maybe. I'm just guessing. This one looks like it's at about 4.3 comma 2.3, I would guess. One thing you'll notice is these parts where they intersect aren't perfectly in these grid lines in the background. So I think that's why they're pushing you to use a table of values. Because you could guesstimate that, but that's exactly what you're doing. You're guessing it. You don't know exactly what that is. And that's what they're promoting you. That's what they're showing you here. One solution is about this, one solution is about that. So what you can do is you can create a table of values. If we go to page 43, they're creating a table of values with all of this. So here is both functions. If x equals 0.5, this is how you read these tables. If x equals 0.5, I can plug that into my blue function. and it's going to output negative 1.5. If I plug it into my red function, it's going to output negative 0.75. So they just keep going. They plug in 0.6, 0.7, 0.8. They're just plugging in a ton of values until they get something that's a little more accurate. I'm going to show you something that's going to be easier than this with this calculator program I'm going to use. But this is one way to do it by hand. What they're showing you here is that between 0.6 and 0.7, it looks like that is getting close to your values. So then they get even more specific. Instead of just going to the tenths place, now they're going to the hundredths place, right? To the second decimal place. So then they find two decimals, 0.69 and 0.7, where they're getting closer and closer. So now they go to the thousandths place, right? So you could see how exhaustive this could be. You could be sitting here for a long time doing this by hand. Again, I'll show you how to do that a little bit easier here in just a minute. Example 4. Use graphing technology to solve your equations. And this is exactly what we want. To me, I think it's important to kind of learn how these functions behave. If we were in person, we would definitely graph these by hand and do it the long way, just like example 3 was showing you with finding the table of values. But as of right now, since we're not in front of each other and we have technology, we might as well use it, right? So this is saying using graphing technology to approximate the solutions to the equation, negative x squared plus 8x minus 13 equals the absolute value of x minus 4. And they want you to approximate it to the nearest tenth. So basically one decimal place. So the x squared function, they're representing it in red. The absolute value function, they're representing it in blue. It looks like there is the first graph. And then they're talking about this intercept right there on the left. And then the second graph is talking about the second intercept that's kind of after that hill goes up and it comes down where it crosses that absolute value function on the right. If we had the calculators in front of us that we have in class, I would show you how to trace that out, and you could trace those functions and kind of put your cursor where those two functions intercept. And that's kind of what it's promoting you. It's pushing you to do right now is to kind of trace that out. But again, I'm going to show you how to do that with Desmos here in just a second. Page 44, concept summary. So this is basically summarizing exactly what we just talked about, everything we went through. I would highly recommend, hopefully when you come out of this section, you're a little more comfortable typing things into a calculator and accessing the information you need. Doing these things with a table of values would suck. It would take a long time to figure out and to complete. So hopefully you can go back through that example that we talked about and just kind of figure out how they're doing this. I'm not expecting you to do that with a table of values. All right. So let's jump over to problem 9 on page 45. So this is going to look a little bit different. I'm going to do most of these problems in Desmos, and I've already got them preloaded in there, and I'll show you what I'm talking about here in just a second. Some problems I'm going to come back and actually write some things, but I don't want to keep flipping back and forth and get you sick between Desmos and then this, and then Desmos and this. So I'm going to do a handful of problems in Desmos, and I think I've just got 2 problems I need to come back here and show you what I'm talking about and draw a picture. So, all right, so we'll start off with number 9. So here's Desmos. Again, this is linked inside Canvas. I think up in kind of the introductory section, I think I have a Desmos calculator link. And if I remember correctly, I think I linked it in your homework section for this week for 1.5. Desmos graphing calculator. If I didn't, just Google it. Desmos graphing calculator. It's the first thing that pops up, and this is exactly what you'll see. You'll see here I've got a ton of stuff loaded already. That's just to kind of save some time. So essentially what I'm showing you right now on my screen is problem number 9. Remember what I talked about when you're looking at problem number 9, negative x plus 4 equals 2, right? That's essentially 2 separate functions and it's just they merged them into one equation. So don't think about that as one equation where you have to solve it. You're literally treating the left side like one function and the right side like another function. And you can see how I have that in Desmos here. The left side was negative x plus 4. The right side was 2. So I put them both on my graph in Desmos. For this first section, when it's just equations, the only thing you're concerned about with equations is where they cross. Wherever they cross, that's your solution. So if I look at these two equations, you can see when I'm talking here, negative x plus 4, you'll notice the icon to the left is red, so that matches up with my red line. Y equals 2, you'll notice my icon to the left is blue, so that matches up with my blue line. All right, zoom in a little bit. And you can see that they're crossing right here. Notice also I'm kind of hovering over there with my arrow and nothing's popping up. But if I kind of hover right over where they cross and click, a little point pops up. And it basically tells you exactly where they're crossing. All right? So I can see, I know the solution to this equation where these two lines cross is 2, 2. So if it was me writing this out, that would be my answer, right? Use a graph to solve each equation. Negative x plus 4 equals 2. My answer would be parentheses 2, 2. Remember, you could also write it as just x equals 2. That's legitimate, right? Because x equals 2 is just this line right here, and there's only one place when x equals 2 where we cross those two functions. So x equals 2 or 2, 2, perfectly fine. This is that part I'm talking about. I'm not going to keep flipping back and forth between my camera and the screen just because I don't want to get people sick. But remember, when I'm telling you the answers are 2, 2 or x equals 2, don't forget, every week I upload this solutions manual, right? This is in Canvas that you can access, and it's telling you everything step by step, right? Here's number 8. It's walking you through all the information. It doesn't just tell you the answer. It's telling you how they got the answer too. Right? Number 7, it's not just telling you, whatever the answer is. It's walking you through it step by step. So make sure you're using this as well. If I say for number 9, the answer is x equals 2 or 2, 2, and you're not sure how to write it, just pull up this answer key, this solution key, and this will show you exactly what I'm talking about. So for here, the answer would be x equals 2. All right, number 10. Number 10 is absolute value of x minus 4 equals 1/2 x. So you can see my absolute value function's green. My linear function's purple. I'm going to zoom out just a little bit so you can see where they cross. Also, don't forget, like I just said, I'm hovering over that line where they're crossing, or at least where they seem to be crossing, but nothing's popping up. You got to click that, and then it'll pop up. It'll tell you what that intercept is. So for here, graph these two functions, graph the left side, graph the right side. So one of my two answers is x equals 0. The other one is going to be x equals 16. Or again, like I said, if you want to write 0, 0, 16, 8, that's perfect as well. That's another way to write it. Okay. How do I know I have two answers versus one answer? Remember back at the start with number 9 that we saw, these two functions only cross once, right? They only intersect one time. So I know there's only one answer. But now with number 10, you could see that these two functions cross twice. So I know that there's two answers. Wherever they cross, that's however many answers you have. Number 11, 3x plus 2. So there is the left side of my equation equals x plus 4. There's the right side. You could see these are both linear functions. They only cross one time, and it looks like they cross at 1, 5. So x equals 1 or 1, 5 would be perfect. Negative 1/4 x plus 6 is the left side of my equation. The right side's 1/2 x plus 3. Both linear functions. Looks like they cross one time at 4 comma 5, or x equals 4. Number 13, 3/4 x is the left side. 2x minus 10 is the right side. Both linear functions, so it looks like they only cross once. And it looks like that value where they cross is 8 comma 6, or x equals 8. However you want to write that, both of those are perfectly acceptable. If you weren't sure if they're going to cross or turn or hit again, just keep zooming out, right? I mean, you can see that these lines go in that same direction forever, basically. So if you're ever concerned, just keep zooming out and you can get a better idea of, do these lines curve back around and cross again? But like we said, linear functions are straight lines. They don't curve back around, so there's no way for them to cross again. And then number 14, absolute value of x plus 8 equals absolute value of x minus 2. So you'll notice that these lines, if I zoom super far out, they will, I mean, they're getting closer and closer to each other, but they will never cross. This side to the left is parallel. They'll never cross each other. They cross this one time right where my arrow's at, and then from there to the right, they're parallel. They never cross again. They have the same slope. So it looks like I've got this one intercept there of -3 comma 5, or x equals -3. All right, so that's all equations. Pretty straightforward. Graph the two sides, graph the left side, graph the right side, and wherever they cross, that's your solution. Inequalities are a little bit more involved, just a little bit. You're still graphing them both. You can see that my parabola there is the green function. Looks like my line y equals 0 is my purple. It's kind of hard to see. I'm going to turn it on and off. You can see it right here. It's on top of the x-axis. Watch, it'll turn purple, right? You can see that coming on. So y equals 0 is literally the x-axis. So that's why it's not standing out very much. So if I kind of center this a little bit. This is very similar to the problem that we saw with example 2A. Very similar to that type of problem. So for number 15, we graphed both sides, the left side and the right side. The left side is my parabola. The right side is y equals 0. But if you look at the problem, it's x squared minus 7x minus 8 is greater than 0. I wish I had a way to draw this on here. You know what? We'll pause for a second. Let's go back to my book and I'll actually draw it here. Uh, 15. So that's kind of the line you saw. Obviously, my sketches suck, right? They're not like perfectly drawn to scale, but you get the big picture, right? You can see that parabola, you can see that line, and there's my function for number 15. Graph the parabola, graph that line, y equals 0. What I want to really emphasize here, and the thing that can be a little bit confusing, is this inequality symbol. That inequality symbol is greater than. When I say greater than, what I'm emphasizing is all of my y values. All the y values that are greater than. So when this is talking, I want to just talk about the y values that are greater than 0. So let's take a look at that. This is my x-axis from left to right, okay? This is my y-axis from top to bottom. It looks like these two functions cross right there and right there. I don't know what the values are. That doesn't really matter right now, but let's just say that they both cross right there and right there. So the only part that I want to identify is every piece of this parabola that's greater than 0. Instead of greater than, you can think of higher than 0. every part of this parabola that's higher than 0. Well, let's look at the 3 parts, because this is part 1, this is part 2, this is part 3. Part 1 is to the left of that x-intercept. Part 2 is in between the 2 x-intercepts. And part 3 is to the right of that other x-intercept. So let's take a look at what's happening in each of these zones, okay? So when is this parabola greater than 0? When I say greater, here's my line right here, y equals 0, where the Sharpie's at. Every part of that parabola that's greater than that line, y equals 0. Every part of the parabola that's higher than y equals 0. Well, if we look in zone 1, it looks like from my line, from this red line, my parabola is greater, right? It's higher than that line. In between my 2 x-intercepts, it looks like my parabola is less than that line, right? In between these 2 x-intercepts, it doesn't matter where I look, that parabola is always less than that line. And then take a look at zone 3. As soon as I pass that x-intercept, it looks like my parabola is back again greater than that line. Okay? So that's important to identify what's happening in each zone. To the left of that x-intercept, my parabola is greater. In between the 2 x-intercepts, my parabola is less. After that second x-intercept, my parabola is back to greater. So for this specific problem, we only want to keep the part of that parabola that's greater than my line y equals 0, which looks like zone 1 and zone 3, not zone 2, because that parabola is less than that line in that piece. So for this problem, I would want to state, let's go ahead and figure out what those x-intercepts are real quick. So looks like one of my x-intercepts is -1, and then the other one is at 8. All right, so here's my x-intercept. I want to keep the part of my parabola that's greater than 0. So I would want to state, I want to keep all my x values that are less than -1. And then same thing with the right side of 8. I want to keep all of my parabola with all my x values that are greater than 8. So that would be my final answer. All my x values that are less than -1, all my x values that are greater than 8. All right, I know that was a lot of description. I won't go that deep into the rest of them, but I just wanted to really explain how those answers are, how you're deriving those answers from that picture. All right, so let's go back and look at 16. So 16, x minus 5 is the left side. -2x plus 4 is the right side. These are 2 linear functions. Same idea though. Same thought process as what we just talked about. The actual function that we're dealing with is x minus 5 is greater than -2x plus 4. So we want to keep every part of this problem when x minus 5, when the black line is literally greater than the red line. I'll say that one more time. We want to keep the part of this problem when the black line is greater than the red line. So just like before, when we had that parabola and that linear function, this is that pivoting point, that point where they cross, just like with the parabola was the 2 x-intercepts that gave us 2 zones. This only crosses at one point. So we basically have 2 zones. The x values to the left of that crossing point and the x values to the right of that crossing point. So it looks like if I'm concerned with the x values to the left of that crossing point, it looks like my red function is greater than my black function. My red function is higher than my black function, which is not what we want. If we go back and look at the problem, it's when is x minus 5 greater than negative 2x plus 4? So when is my black function greater than my red function? And that looks like it's happening after this intersection between these two functions. Because take a look, if I pick any x value that's greater than 3, take a look at like 7, right? Here's x equals 7. It looks like my black value is greater, or my black function is greater than my red function, right? What about when it's 12? My black function is greater, it's higher than my red function. So as soon as I pass that x value of 3, that's when my black function is greater than my red function. So my answer with this one would be when x is greater than 3. (17) x squared plus x minus 6. That equals, and then the right side is 0. So the left side is the blue part, the right side is the green part. So this is very similar to the problem that we saw back a second ago with number 15. Number 17 is x squared plus x minus 6 is less than 0. So pretty much the opposite of 15, the one that I drew out for you. This has two x-intercepts, just like with number 15. It crosses at negative 3, 0 and 2, 0. So if I take a look at zone 1 to the left of this x-intercept, this looks like my blue function is greater because it's physically higher than my green function. So over here in zone 1, this is x squared plus 6 plus x minus 6 is greater than 0, which is not what we want. The problem says x squared plus x minus 6 is less than 0. Take a look at zone 2, between my two x-intercepts. My parabola, that blue function, is all below that green line. It's all less than 0. So unlike problem number 15, I want to keep zone 2. So my answer for number 17 would be basically every x value between negative 3 and positive 2. And I would write that like this. Negative 3 is less than x, which is less than 2. If it's kind of hard to follow me when I'm just kind of saying the answer versus writing it down, remember, you've got the solution. Bring this up. What number are we on? 17. Pull up number 17, and you can see exactly how to write it right there. Don't let this deceive you. Look at that. It says, so the solution is, their negative is up here. It is with the problem. So it is actually negative 3 is less than x, which is less than 2. That should be down here so you don't lose track of it. But so if you have a hard time just kind of following me with when I say the answer, just pull up this answer key, this solution, and you can see how it's supposed to be written. Number 18, x squared plus 2x minus 8 is less than or equal to 0. So my purple line is my parabola. My black line is my linear function, y equals 0. Let me turn that on and off for a second so you can see where it's at, right? Y equals 0 is just my x-axis. It's the same thing. So the inequality symbol is x squared plus 2x minus 8 is less than or equal to 0. So we want to keep the part of the parabola that's less than, that's lower than this line, y equals 0. So again, over here in zone 1, it looks like that parabola is greater than that line, right? It's physically above it. Between my two x-intercepts of negative 4 and 2, it looks like my parabola is less than. It's all below the x-axis. It's all below y equals 0. And then on the right side in zone 3, after you get x equals 2, it looks like my parabola is above that line, y equals 0. So for number 18, when is that parabola less than or equal to 0? My answer would be all my x values, including and between -4 and +2. Why did I say including? Well, again, the inequality symbol they're using is less than or equal to. So you want to make sure you include those values. Another way to write that out, the way you should write it out, is -4 is less than or equal to x, which is less than or equal to 2. That's how you should write that answer. -4 is less than or equal to x, which is less than or equal to 2. Number 19, -x squared minus 2x plus 15 is less than or equal to 0. My parabola is the red line. My linear function is the blue line. So I want to know when that parabola is less than or equal to that line y equals 0. So when is the red function less than or equal to the blue function? Again, we could split this up into 3 zones. There's my x-intercept. So in zone 1, over here to the left of that x-intercept, it looks like that red function is less than because it's all below it. Notice if I choose x equals -5, I have to go down to hit that function. So all my x values that are less than -5, that's when my parabola is less than that line. In between my x-intercepts, my function, my parabola, the red function is above, it's greater than the blue line. And then in zone 3, after that second x-intercept of x equals 3, we're back down to when that red function is less than that line. So we want to keep all parts of the parabola that are less than or equal to 0. So I'm going to say my answers are going to be x is less than or equal to -5, because I want to keep all of this over here to the left. Because as soon as I pass -5 to the left, that's when my parabola is less than that line. And then the other piece would be I want to keep all of my x values that are greater than or equal to 3. Because again, as soon as I pass 3, that's when my parabola is back below that line, y equals 0. Number 20, -x plus 5 is less than 1/2 x minus 1. So I'm going to keep the parts of my green function that are less than my purple function. Here's where they cross at 4, 1, and you can see every x value to the right of that. As soon as you pass x equals 4, that's where my green function is less than the purple function, right? The purple function is right here, and you have to go down to hit that green function. So as soon as I cross that x-axis or that x-intercept of 4, that's when my green function is less than the purple function. So for number 20, I would say x is greater than 4. X is greater than 4. Not greater than or equal to, because the inequality sign they're using is strictly less than. -x plus 5 is strictly less than 1/2 x minus 1. All right. Number 21, Cindy is longboarding 6 miles ahead of Tamara. Cindy is traveling at an average rate of 2 miles per hour. This is very similar to example 2b, to be more specific. Let's take a look at this. Let's look at 2b, because I've got it written out here. Okay. Cindy is traveling at an average rate of 2 miles per hour. Tamara is traveling at a rate of 4 miles per hour. Let X represent the number of hours since Tamara started longboarding. When will Tamara be ahead of Sydney? Write an inequality to represent the situation. So again, just like we've been doing so far, you want to create kind of a two-piece inequality where the left side represents Cindy, and then the right side represents Tamara. Okay? And that's exactly what I've done here. I've just kind of drawn a little bit of a picture. It said that Cindy, one of the first parts of it was that Sydney, I don't know why I have such a hard time saying that, Cindy was 6 miles ahead of Tamara. So I just kind of drew a little line just showing that Cindy was 6 miles ahead of Tamara. The next piece of information it gave me was how fast they're both going. So it said Cindy was going 2 miles per hour, Tamara was going 4 miles per hour. So that's all the information they gave us. So what I want to do is I want to create, I'm going to say the left side of the equation is going to be Tamara, and then the right side is going to be Cindy. And then we're going to have some sort of inequality symbol in the middle. Okay? So Tamara, they're saying Cindy was 6 miles ahead. So I'm going to go ahead and include that with Cindy. Tamara, the only piece of information they're giving us is that she is going 4 miles per hour. So I'm just going to say that that's 4x. Cindy, they're telling me she's going 2 miles per hour and that she's already 6 miles ahead of Tamara. So if I want to say that Cindy's going 2 miles per hour, I'll say 2x. But since she's already got a head start and she's already 6 miles ahead, I'm going to say 2x plus 6. The last piece I need is this inequality symbol. Let me go back and reread my problem. Let X represent the number of hours since Tamara. When will Tamara, I don't know if I'm pronouncing that right, be ahead of Cindy? So when will she basically pass her and be ahead of her? So I'm going to say, I'm going to represent that with greater than. Since they want to strictly say when will she be ahead of Cindy, I want to say greater than. Not when will she meet up with Sydney. If that was the case, then we'd use greater than or equal to. But when is she actually going to get ahead of her? I want to use strictly greater than. So let's go back to my graph. I've already got this graphed in there. 4x and 2x plus 6. There's 4x is the black line. 2x plus 6 is the red line. It looks like if they're both going, they cross at 3,12. So essentially, let me see if they're talking about hours or minutes. Let X represent the number of hours. So they're saying at 3 hours, that's when the two of them are going to meet up. That's what this graph is representing. But remember what the question they asked is, when is she going to be ahead of Cindy? When is Tamara going to be ahead of Cindy? So that's after this point. So as soon as you pass X equals 3, that's when the black line is above. That's when the black line is greater than the red line. So for number 21, our answer would be when X is greater than 3. When X is greater than 3. If I said when X is greater than or equal to 3, now the question's changed. Now the question is, when will Tamara meet up with Cindy? When is she going to catch her, right? But it wants to know when she's going to be ahead of her. So you have to say when X is greater than 3. All right. 22. Use a graph and tables to solve the equation. Again, I'm not expecting you to do tables like they did in that problem. I am not going to ask you to do tables like in that problem, in the example problem. I think that's a crazy amount of work, so I'm just going to use the graph. So my function for 22 is x squared minus 8x plus 5. So that's the blue function. And then the green function's x plus 3. You could see this is a parabola and a linear function, and they're crossing at some decimal places, not nice even numbers. But if you take a look at Desmos, the cool thing, the thing that I wanted to show you, the reason why we don't need a table is because if you just click on that point of intersection, it's going to tell you up until the thousandths place, so 3 decimal places, it's going to tell you where they cross. So for number 22, they want to know when the two are equal to each other. So I would either write that point, or I would just write x equals 0.228. And then the other intercept, or the other intersection part of it between the two graphs is either that point on the screen, 8.772, 11.772, or you could just state x equals 8.772. Technology definitely saves you some work. Number 23, 1/4 x plus 3. That's my purple function. And then x squared minus x plus 2 is my black function. This is still equations, so I just want to know where they cross. So x equals negative 0.554, and x equals 1.804. Number 24, 2x squared minus 5, so that's my red function. Negative x squared plus 2x minus 1 is my blue function. Let me center this a little bit better. Again, click on that point of intersection. X equals negative 0.869, and x equals 1.535. Number 25, 3x minus 4. So that is going to be my green function. And then 1/2 times the absolute value of x minus 5 is the purple function. Here's the one part where they cross at x equals 1.857. Again, this section is telling you to graph it and use a table. If you wanted to create a table, that's awesome. Feel free to. You can kind of use the example in the beginning of the lesson to model what you're supposed to be doing. But essentially what you're doing is just guessing numbers, and you keep plugging them into the function. And then if the output gets closer and closer and closer, you keep guessing more numbers. But if you overshot it, that's when you get more specific. So you can kind of see that example back with the one that we saw earlier with example 3. They start off by guessing numbers with tenths place, and then when they narrow it down, they move to numbers in the hundredths place, and then when they narrow that down, they move to numbers with the thousandths place. So you could see how much work that might be if we were to do that. Just kind of know how that's supposed to, what they're doing there, and understand what they're trying to say. I'm not expecting you to do that. All right, 4 more. 26, x squared plus 6x minus 8. And then equals, so no more inequality signs, so that's nice. The absolute value of x minus 1 plus 3. So we are looking at the parts where these two functions cross. You can see they're crossing in two intersection points. X equals negative 8.424, and x equals 1.531. Number 27, absolute value of x plus 2 minus 6. So that's my blue function. And then my green functions, x squared minus 7x minus 2. You could see that they're crossing here at a couple places at x equals 0.258 and at x equals 7.742. (28) 1/5 times the absolute value of x plus 2. And then the right side, 1/5 times the absolute value of x plus 2 minus 3. And then the right side of the equation is the negative absolute value of x minus 1 plus 5. So same idea, since it's equations, you just care about where they cross. So x equals negative 6.167 and x equals 7.167. And then the last problem, number 29, x squared plus 3x minus 7, the red function. The blue function's negative 2x squared minus 6x plus 9. Again, these are both equations. In between the two functions is an equal sign, so you just care about where they cross. At x equals negative 4.254 and x equals 1.254.